Okay, so I'm going to try yet another little configuration. I realized I can just carry this thing around, talk to you guys, and still write with the high-resolution pen. So we don't have to worry about the camera capturing the board, yet I'm still moving around so that you're not dozing off some person just sitting on a stool in front of class. So I think this is going to be a good arrangement. I think it'll be better, the best of both worlds. Okay, so today we're finishing out all of the discussion on partition functions for the molecule. And so we've covered translational motion and the partition function related to that. We've covered rotation, and today we're doing vibration and electronic. Electronic is the easiest because we really don't have any excitation thermally of any of the electronic states. And so Q is 1, essentially, right? If you're in the ground state for any of your systems, then Q is the count of number of populated energy levels. And so if everything's in the ground state, then you have one energy level that's populated, so it's just 1. But let's look at vibrations. So reviewing a little bit, remember the harmonic oscillator potential for vibrational motion. That's the assumption that these stretches, bond stretches and bends are like a mass on a spring. And so they have that harmonic potential, and the quantized energies are an equal ladder of states. And so there's the same spacing between each of the energy levels. That's not the case for translational motion. It went as n squared. So the energy levels were not equally spaced. Same thing. All right. And then the same thing for the rotational energy levels. They went as j squared. It was j times j plus 1. So there was a linear component, but there was also a quadratic component. Whereas in the vibrational energy equation, you see it's just the quantum number v plus a half. So it's linear in v. So when you go from 0 to 1 and 1 to 2, you have the exact same energy spacing. So we can go through this partition function using the Boltzmann distribution with this energy equation inside. Okay. Now this harmonic oscillator potential function fails with low frequency stretches, if they have big masses and weak bonds, and it also fails with internal rotation. So what is internal rotation? Well, that's that thing we modeled on the homework and then in this week's lab with the rotation of the ethane molecule, dichloroethane, where you have the molecule rotating around the carbon-carbon bond. So at maybe the first the ground state and maybe the first excited state could be modeled with a harmonic oscillator, but because you have those partial barriers, they don't go up to infinity. They're not a harmonic oscillator. You know, these potential barriers go up to infinity in the harmonic oscillator. That works really well for like a hydrogen stretch, where it really takes a lot of energy to pull that hydrogen off. And so it's very harmonic in its character. But when you have big masses, like maybe the iodine bond, that's going to be showing a lot of anharmonic nature, and then internal rotation is another classic case where the harmonic oscillator assumption fails. Okay, so that partition function is the sum of all of the Boltzmann factors. The degeneracy for all of these states is 1, and so that G of V is 1, so it's essentially not in the calculation. And if you look at this, we see that this same term, when it's if we set 0 here at V equals 0, then the first term is e to the minus 0, and so then the V equals 1 state is here, E1, and then the second one is E2, but that is twice the energy of the first vibrational state. Somebody see that? It's 2, since it's equal spacing, this next one would be 2 times the energy of E1. This next one would be 3 times the energy of E1. Okay, and so we have this sum that is the sum of this series that goes up in terms of its exponent. Okay, that's if we set the 0 energy point at V equals 0. We have a couple of options in this case. We could set the 0 here, in which case this calculation is very easy. Okay, it behaves like you would expect. If we're at extremely cold temperatures, all of the excitation, there wouldn't be any excitation, everything would be in the ground state, and our Q would go to 1. So setting V equals 0 equal to 0, that's the best option. Okay, it makes the most sense. Occasionally, when you're doing chemical reactions and you're calculating with Gaussian, and you want to calculate this 0-point energy, the difference between this bottom point and the first energy level, in order to calculate the total energy of the reactants and subtract the total energy of the products, it makes sense to set the 0 energy at the bottom of this harmonic potential. Okay, and so we have two choices: 0, V equals 0, and BOT for bottom. Okay, and we'll see those in the output of the Gaussian file. So I'm just sort of putting a marker here so that you could say we decided to where we set the 0, where we say energy is 0. We have two choices, and Gaussian provides the information for both. And so those are our two choices. Most of the time, especially if you're doing it by hand, you're going to use this one. The ground vibrational state is going to be set to 0 energy. Okay, so this is fortunate because this is an infinite sum over all of those energy levels, and some infinite series converge. And so when we have equal energy spacing relative to the ground state, we have this sum here. And if we look at this, let me see if I can do this with my pen. Okay, if this piece is x, so if we look at this piece here as x, so this is x, this is 1, okay, and this right here, minus, forget the 2, okay, that is x squared. You see everything that I've circled is the same as x, and then this is x cubed. Let's get the 3. And so it goes on and on and on. Surely you recognized that, right? And surely you remember that this series converges. So if you have this infinite series, it goes up and up and up, and then it converges to this point here. So this is the solution to the partition function. So we don't have to assume that the vibrational spacing is infinitesimal at any given temperature or anything like that. This partition function actually converges to this result. And so this is an exact solution. This right here, this HC nu, that's just that E1 that we were seeing up here, this E1. Okay, and so that's beautiful. Now for the vibrational energy, in fact, we could look at this, and this HC nu over K, that's the vibrational temperature, and we could just divide that by T. So if we calculate vibrational temperatures, compare them to T, put them in the exponent, and 1 minus in the denominator and under 1 in the numerator, then that is the exact solution for the vibrational partition function. So that's fantastic. And this, I doubt that you recognize it, but if you look at Planck's solution to the blackbody radiation curve and that UV catastrophe, this is the equation. There's a few other constants thrown in there to make the units work out, but this is the equation. And where did he get this? He got this from Boltzmann. And so Planck was bothered by the blackbody radiation. He knew that there was, it had to be solved. The Rayleigh-Jeans law, so just to refresh your memory, blackbody curve looks like this. The Rayleigh-Jeans law went to infinity, okay? And so when your solution goes to infinity and the data goes to 0, that's called a catastrophe, okay? So in the UV region, the Rayleigh-Jeans law went to infinity, and the real distribution went to 0. And then Planck was saying, what if I use this idea of quantized states in a harmonic oscillator? So let's model material that's heated up and emitting this blackbody radiation. Let's model it as a bunch of little vibrational oscillators emitting light. what do we get? Well, he used Boltzmann's distribution, which used this Converge series, and it fixed the problem. So it was really Boltzmann that fixed the black body radiation problem, but he didn't apply it to that. Planck applied it to that, so Planck gets credit for it, which rightly so. But the problem buried in that solution was that energy is quantized. And so that's what really, really bothered Planck. He used what later became his constant in solving the problem. He called it the elementary quantum of action. He was saying that this little piece of energy that is the quantized energy helped solve black body radiation. Was that just a coincidence? Was it a mathematical trick? And then later, when they did the photoelectric effect, so this was number of electrons and frequency. There was a linear relationship. Well, number of electrons, I'll say kinetic energy of the electron. The slope of this line was Planck's constant, so E equals h nu. And so that's called the Planck equation. And so his constant showed up in two different places that were independent of each other. And so when he determined that was the slope of the kinetic energy line in the photoelectric effect, he said, oh, well, the Planck's constant then is something, a part of nature, essentially. So the vibrational partition function, again, is shown here. We can look at this in terms of different temperatures. And so when we have this term beta E, remember beta is 1 over kT, so this is the energy spacing over kT. And this is saying that when that energy spacing over kT is roughly 3, that means the energy spacing is 3 times the temperature that you have. And so in this case, the temperature is 1/3. I'll draw a little, like the little surface of water in a bathtub. I always think of the room temperature or the temperature the system's at is like the water in a bathtub. How deep is it? And this energy spacing is 3 times the amount of thermal energy that you have. And so most of the molecules are in the ground vibrational state, and a few are in the excited state. Okay, and so our Q is 1.05. So we have about like a 5% chance of being excited. In this case, beta E is 1. So then we've warmed the system up. So now the energy level spacing and the thermal energy are the same. And so now we're getting excitation to the second level and a little bit to the third. And we can see that Q has gone up to like 1.6. 0.7, gosh, I don't know how to do that. So this spacing is 70% of the thermal energy, so it's probably right there, right? Does that seem reasonable? And we get even more excitation, so 1.99 is our Q. Notice how this makes it seem like there's 2 energy levels populated, right? It's not that sharp of a sum, right? So we're absolutely, it's definitely telling us we have definite excitation into the second energy level, but there's also some minor, excitation in the third, fourth, fifth, and sixth. Okay. And then in this case, the energy level spacing is about 1/3 of the thermal energy. So that's 1, 2, 3. So our thermal energy bath is up here. And this is showing about 4 energy levels that are calculated. So it is kind of nice. It's hitting that, we definitely have 3 levels below our thermal, bath level. Here we have 2 levels that are below our thermal bath level. So it's telling you, again, how many levels are guaranteed to be populated. And so that's a way to think about this idea of temperature in the Boltzmann distribution. So that's what these probabilities are being shown by these blue bars. we still have the same rule of thumb that this energy spacing or these quantum effects kind of disappear when the thermal energy gets to be 10 times that difference. And so 1, 2, 3, 4, 6, 7, 8, 9, 10. So when the thermal energy is up here, then we call that mode activated. So that's activated. That's not going to happen in something like a CH stretch, but it will happen maybe in the bending of the whole molecule. So when you get into the vibrational levels, the bigger the molecule, the more vibrations are active at room temperature. If you've got a small molecule, almost really a small molecule like methane or something like that, none of the vibrations are active. It takes a big molecule and really heavy atoms for those vibrations to be active. We'll see in another couple of lectures why that's a big deal. At this point, it's not quite clear, I'm sure. Now, the probability of any given level, again, is the energy of that level divided by Q. So we can calculate the probabilities of any of these blue bars using that. Okay. I'm just kind of walk through that whole thing. Okay, so this harmonic oscillator partition function, we can again take this energy here and put it in terms of temperature so that we have easy calculation, the vibrational temperature divided by the thermal temperature. Notice how this is looks like a linear function essentially, and it's going to 0, and then right when it gets down here, it takes a turn and goes to 1. Okay, so that's a nice little behavior. And so you should be able to look at this equation and do this kind of analysis. So as temperature goes to 0, how do we work our way out to know what happens to our vibrational partition function? So this is one of the ways or analyses I would like for you to be able to do. So as this goes to 0, all right, this goes to 0, what does this whole fraction do? This whole fraction does what if temperature goes to 0? It's in the denominator. So if I'm dividing by something that it goes the other direction. What is it? It goes to infinity, right? Okay, so the whole fraction will go to infinity. You got that? Yeah. All right. So you work your way out. So I would say, how does the partition function depend upon temperature? Work your way out. Start at temperature and say, okay, it depends on temperature. What happens if temperature goes to 0? Then the fraction, just do it a step at a time. The fraction goes to infinity. What does this e to the minus infinity give us? E to the minus infinity. Okay. Do you know your exponential function? So just think about this. This is e to the x. Okay. Minus infinity. Okay. So e to the minus x. Let's do that. It looks like this, doesn't it? It's an exponential decay. So what happens when it goes to minus infinity? What's that curve doing? Yeah, it goes to 0. So this piece here goes to 0. And now 1 minus 0 is 1, and 1 over 1 is 1. So then this whole thing then goes to 1. So that's all of the steps I'd like for you to be able to do. So I've basically got them written out in case I make a mistake. Right? Temperature goes to 0, that fraction goes to infinity, then e to the minus infinity goes to 0, and then q goes to 1. So you should be able to do that. Given any equation, you should be able to say, okay, how does this equation depend upon temperature? And so you look at the limits. You say, well, as temperature goes to 0, this thing approaches 1. Let's do the other side. As temperature goes to infinity. You may want to, like on your notes, put this off to the side since you don't want to erase. And I've got it written out, but let's do it by hand again. So as temperature goes to infinity, now we have infinity in the denominator. So this fraction with infinity in the denominator goes to 0. Now we have e to the minus 0. So that piece goes to 1, because anything raised to the 0 power is 1. And then this denominator goes to 0. So Q goes to infinity. Everybody follow those steps? It's not that bad. It's just you got to be systematic. So as temperature goes to infinity, this fraction goes to 0. As that fraction goes to 0, this e to the minus 0 is 1. And we have 1 minus 1 in the denominator, so that blows Q up. So temperature goes up, Q goes up. Temperature goes down, Q goes to 1. And this is just showing this is a temperature scale, but it's divided by the vibrational temperature. So this is the behavior for any vibrational mode that's a harmonic oscillator. So if you have a CH stretch or a carbonyl stretch or any of those kinds of stretches, whatever that vibrational temperature is, this is what it looks like when temperature goes to 0. When temperature is 5 times that vibration, when temperature is 10 times that vibration, it just looks like a nice linear line as it goes up. Okay, so this total vibrational partition function without 0-point energy, I mean, it does look linear. Like when we plotted that function, it looked linear. And so at very high temperatures, it essentially becomes this temperature over theta V, even a more simple calculation. And so this is a nice approximation of this exact equation. And so when we say when temperature is 10 times that vibrational temperature, we say that the vibration is activated. Now here's something that I guess I'm not quite sure why students find it hard to remember, but think about a molecule. There are 3n minus 6 vibrations. And so for the vibrational partition function, there are that many partition functions. Every vibration in the molecule has a separate partition function. Like I could be excited in this really bendy mode, and it could be really excited because it's a low frequency vibration, but my CH stretch is still in the ground state. So every individual vibration has its own partition function. Make sense? Just like every rotation, rotating around X, rotating around Y, rotating around Z, all 3 of those are their own partition functions. And then all of the translational ones, translation in X, translation in Y, translation in Z. Now this is another important principle, that the total partition function is just the product of all of the individual ones. And so Q, let's just do Q total. Well, it's really leaning. Let me try to stand here. I'll stand out of the way. Let's see if I can get this. So this is the partition function for translation times rotation times vibration. And this one has 3 terms, this one has 3 terms, and this one has 3n minus 6 terms. And so notice how it all adds up to n, 3n. I mean, every atom in the molecule has 3 degrees of freedom, and so it can translate, rotate, vibrate. And so we have all of the motions taken care of, and we can store energy in every one of those different energy levels. So let's look at the Gaussian output. So last time we looked at the rotations. and we had the rotational temperatures here. It looked like what we call a coincidental symmetric top, because the hydrogen rotating around the axis of the molecule didn't really change its masses very much, because hydrogen's so light, and so it really looks kind of like a diatomic. Okay. And so then here's the vibrational temperatures. Now, how many vibrations should we have? They don't always list all of them. They list the lowest ones in the molecule in Gaussian. So we have three atoms. So 3 times 3 minus 6. So 3 times 3 is 9, minus 6 is 3 vibrations. And that's how many vibrational temperatures we have. So can you tell me which is which? Like this 5,000 Kelvin, which vibration is that? What are the vibrations in this molecule? Let's back up to that. So can you tell me the 3 vibrations that the molecule has? It's nice that it's asymmetric, so that there's, all the vibrations are isolated from each other. It's not like benzene where all the hydrogens couple with each other in all these different combinations. Austin's doing it. He's got the atoms. So what's just pick one. What is the vibration? See if we can figure out what they are. So this is, you'll see that I ask you a lot of these review questions, because whenever you sweep the floor, you don't just sweep once and call it done. You always reach back and sweep the floor again while you're moving forward. And so that's what we need to do when we teach. So I always reach back, like right now, I'm reaching back to organic. What is a CH stretch? Is that high frequency or low frequency? Can you picture an infrared spectrum in your mind? Where is the CH stretch? And look at the x-axis in your mind and see if those are big numbers or small numbers. Yeah, the CH stretch is a high frequency stretch. Okay, and it's around 3,000 wave numbers. So we could figure out if we have a 3,000 wave number stretch, so CH stretch. Let's divide that by Boltzmann's constant over Hc, which is 0.695. So I've got something that's 3,000, and I'm dividing by something that's slightly less than 1. What's that going to do to the number? It's going to make it bigger. And so that's going to be 5,000-ish. And so that's what we've got here. So that's the CH stretch. Now, in terms of which of these is the carbon-chlorine bond or oxygen, I think this is oxygen. So I've been talking about the CH stretch, but this is the OH stretch. Okay, still a very high frequency thing because it has such a light mass. Here's the OCl stretch. So we have this stretch here. We have this stretch here. What's our other vibrational mode? Yeah, it's a bending motion. So it would be keeping the bond lengths the same. It would be this bending motion. So this little hydrogen pivoting around this bond. So you could look at it in terms of this angle. So this angle here, theta, would increase and decrease. So that's the bending motion. So you have 2 bond lengths and an angle. Those are your 3 vibrations. It's exactly the same as what we have for water, right? We have the symmetric stretch, the asymmetric stretch, and then the bending. Water's a little more complicated because you have 2 identical bonds, and so they kind of talk to each other. They have nearly the same frequency. So at least we have an understanding of the number of vibrations. These are the different temperatures. If you were to twist my arm and make me make a choice, okay, because of that big fat chlorine, I would say this is the O CL stretch. And that this was the bend. But I could be wrong. No, actually, I did. I think I did. I would change my guess, okay? Because again, this is the biggest, heaviest atoms, and so that's going to be probably the lowest frequency mode, and that the bend with this really light hydrogen is going to be higher frequency. So if I had to go animate this, I could see if I was right or not. Okay. And so we review, it has 3n total degrees of freedom. 3 of those are translation, 3 are rotation, and then 3n minus 6 are the 3 vibrational frequencies. Now, Gaussian calculates the partition function. And so we have all of these pieces. We looked at translation and rotation last couple of times. We have the calculation for vibrational motion done 2 different ways, like I said. And so if we take into account the vibrations, this would be with B equals 0 being our 0 point energy where we put zero energy. This would be the partition function. And you see it's not very excited because these vibrational temperatures were 1,000, 1,800, and 5,000. And what's room temperature? 298. So we're nowhere near populating these. So if you were just shown this and you had to guess what would Q be, it would be roughly 1 for each of these. So 1 times 1 times 1. So your total vibrational Q would be 1 cubed. Okay. And so that's what we have here. V equals 0. It's very close to 1. It looks like 0.1, but remember this crazy scientific notation. It's 0.1 times 10. Okay. So that's what you would estimate. Now, if you set your vibrational, if you set 0 at the bottom of that vibrational potential, then this is saying that you're not even populating the ground state, okay, which is strange, right? But that's what this is. You see, this is 0.1 times 10 to the minus 5. And so it's saying there aren't even any molecules in the ground state. So once again, this is going to be useful only for other, calculations where you're comparing molecules to molecules. And you need to pick a 0 on your energy axis. You need to pick a 0 that applies to both molecules. And so you can't do that if you have a 0 at their vibrational ground state because they both have different vibrational potentials. And so it's a special case, and so Gaussian it calculates that for you, but we don't really use it. Okay. And so what's this total? The total is the product of all 4 of these: the translation, the rotation, the vibration, V equals 0, and the electronic. And that's the total. And so we can look at that total. Here it is, just getting rid of that crazy scientific notation. You can see all of the different pieces. So the translational, which is huge, times the rotational, times the electronic, times the vibrational gives you this number here. And so the electronic partition function, since KT is much, much less, if KT barely excites some of the vibrational motions, the electronic differences are absolutely huge. And so you really aren't going to get thermal excitation in any of the electronic states. So the electronic partition function is simply the degeneracy of the ground electronic state, which is almost always 1, but there are some molecules where it's not 1, like nitric oxide. You have a free electron, it has a doublet as its multiplicity, so its ground state has a degeneracy of 2. And so that would double your partition function. Now, why is thermal energy never really stored in electronic states? Think about this. This would be in your electronic states. If you have chromophores and so on, they show up in the visible region. If they don't have like conjugated extended electron clouds, like long chains or aromatic rings and so on, then they're colorless, right? You don't see any kind of visible absorption. Where are those homotolumos? They're in the UV region. So even in the extended case, like beta carotene, where you got this long extended chain in the long box, and you get a peak in the visible region, you get a red color for the molecule. So, in the visible region, this would be the longest wavelength that you would have a homolumo gap. Well, let's convert this to temperature. So 1 over that, or wave numbers, 1 over that 700 nanometers, and converting from nanometers to centimeters, we get 14,000 wave numbers. And remember, room temperature is 298. So this difference in terms of wave numbers is 14,000 wave numbers. Dividing that by that Boltzmann constant over Hc, we get a temperature of 20,600 Kelvin. So it would take 20,000 Kelvin to excite the homolumo with a 700 nanometer wavelength. Molecules aren't going to survive that. Why not? Well, think about the vibrational motions. If we get to 20,000, we've started exciting those vibrational motions and tearing the molecule apart. Some of those weaker bonds are going to go anharmonic, and they're going to come apart. So the molecule is going to absorb a lot of that energy as you're approaching 20,000 Kelvin, and it's just going to decompose. Another way to say, even if you could withstand that temperature in your vibrations, what's going to happen to the electronic levels when I start exciting electrons to antibonding states? So I take electrons from bonding states and put them in antibonding states. Now it's excited, and our bond orders go to 0. And so then the molecule falls apart. So there's just really no thermal way to excite the electronic energy levels without destroying the molecule. It can happen. You can excite. I mean, you can get to 20,000 Kelvin, okay? But that molecule is not going to stay intact. It's going to completely fall apart. So you wouldn't have a stable molecule holding that much energy because it would fall apart. So this is a bit of review here. Here we have our translational piece. And there's our volume. Remember, it was V over lambda, right? And that we changed that V with the ideal gas law. This is the rotational piece. We have our rotational temperatures, all 3 of them for the 3 rotational axes. This would change if it was a linear molecule. We would only have 2 of those, and it would be temperature squared in the numerator. Okay. The sigma is that symmetry number in case we have a highly symmetric molecule. And then this last piece is the vibrational piece, which we have that vibrational temperature divided by the thermal temperature here in the denominator. There's 3n minus 6 of those. And then we have the electronic piece, which is the degeneracy of the ground electronic state. So this is what Gaussian does for us. Thanks so much, Gaussian, because it's really tedious. And so just, I guess, a couple of take-home lessons. The total partition function is the product of all of them. If they all go to 1, then the product goes to 1. So there's no way to get it to go to 0. All right. And what else? I think that's it. So let's go ahead and do the Kahoots on vibration and rotation. So we'll do a little review on the rotation one. See if this will work. Okay. And I'll find my mouse. Yeah, good. Okay. And classic button. It's a QR code, but I don't know if your camera can see it from that distance. Cassie's got the quick thumbs today. It's everybody, yes? Okay, so which of these molecules has the smallest rotational constant? Okay. The smallest rotational constant. This might be a repeat of one we did last time. Did we do? Yeah, we'll see. Okay, very good. So the heavier masses, the mass is in the denominator, and so it should be a small rotational constant for heavy masses. I think we did this one last time. We'll just read it. Does rotational temperature go with the rotational constant or against it? And it goes with it. Okay. So if you have a higher rotational constant and you have a higher rotational temperature, that's related to the energy level spacing. So, why does hypochlorous acid appear to be a symmetric top? Yeah, I know we did this one. Do you want to skip this one and go to the next Kahoot, or we'll just go through it? It'll be good review. Nice. Okay. It's almost a diatomic because that hydrogen is such a tiny mass. Okay, Austin, you're killing it. What motion corresponds to the large rotational constant in HOCl? If I get a perfect score, I'm going to take a picture. Did we do it? Yeah, we did. All right, good. Got the results here. Grams, perfect score. All right, I missed Austin. I think we were behind the faucet. So there we go. 1, 2, 3. Nice, okay. Gotta hit 2 clicks every time, okay. True, false. Temperature reaches 0, the partition function goes to 1. It's gonna be. Yep. And last one. How many rotational degrees of freedom are there in a nonlinear molecule? I beat that into you, I think. Yes, perfect score. Good job. I like their little characters. They did a good job on that. I always wanted to be able to draw like cartoon characters. The ability to draw is trash. I can draw molecules, but I can't draw. I guess it's what you practice the most, right? My inorganic professor could draw 3-dimensional crystal shapes on the screen, on the chalkboard, and I would just see it like, man, I want to draw like that. So I practiced on that. It was good. Okay, so now let's go back to the PowerPoint and do this other Kahoot. Come on, where's my mouse? Oh, that's right. Good. Good old Doge. Okay, there's our new game pin. Yeah, we got the classic song now. I like the last set of characters better. These are crazy. You got a little Einstein here with a green face. It's nice. Okay, new questions for us. At what minimum temperature is a vibrational mode activated? You heard me say that, but I don't know if you remember that. Okay, kind of a spread here. It's the blue one. It's when the temperature is 10 times the vibrational temperature. Now, who can tell me in their own words what I mean by activated? I know this is a tough concept, so I want to focus on it a little bit. If you want, I'll give you a small piece of vocabulary to use in your definition. So, quantum effects. What do I mean when I say a mode is activated? And you can use this idea of quantum effects in your response.
Does it mean whenever the vibration changes?
You're on the right track, but that happens below this temperature. Okay? So when you cool things down, you're able to more easily detect quantum effects. So conversely, what happens when we activate a vibrational mode?
No longer detect quantum effects?
Yeah, we don't see the quantum effects. They disappear. They get lost in the action, if you will. We have so many transitions between levels that the quantum effects essentially are not easy to detect. Okay. Think about that black body radiation curve. That is a spectroscopic measurement, but you don't resolve individual transitions. You're just looking at the behavior of the whole substance because it's so hot. Okay, and so that's an activated vibrational system. Okay. Oh, good. I can use this. Go to the next one. For the HOCl molecule, the 3 vibrational temps were over 1,000 K. So what is Q vibrational? So if you didn't have time for your calculator, and you saw that the 3 vibrational temps were over 1,000 Kelvin and you're at room temperature, you had to pick a Q. What Q would you pick? Okay, it's going to be 1 because the vibrational temperatures are here, your room temperature is down here, everything's in the ground state. So for each vibrational mode, Q is 1, and the Q total is all of them times each other. So Q1 times Q2 times Q3, 1 times 1 times 1. So, pretty good. Okay, a little shake up there. Look at that. Why is the electronic partition function almost always 1? Pick your best or favorite one. There may be more right answers than just one. Yeah, so there's 3 right answers. Not all the energy is stored in translation and rotation. Some of the energy is stored in vibration, but these 3 are definite. The electronic energy levels are too high, the thermal excitation is unlikely, and the molecule would decompose. And so any one of those would be a decent answer for that. Okay. Number 4, the total partition function is the blank of the trans, rho, vibe, and electronic partition functions. All right, the majority got it right. Here it's the product. So it's Q vibe times Q rho and so on. And even in the individual pieces. Now, what's the total energy by contrast? So this is the partition function, not the energy. This is the number of populated states, right? And if I have a bunch of rotational populated states times the vibrational populated states and so on. The reason it's a product is because it's probabilities, right? So if I have a 50% chance of being in an excited state here times a 50% chance of being in an excited state in the vibrations and so on. So for each individual molecule, it's the probabilities times each other. But what is the energies? How would I calculate the total energy? Is it a product, a sum, a maximum, minimum? What would it be for energy? Energies are sums. So it's the energy. So if I'm a molecule and I have energy in my translations, and then I'm going to add in my rotational energy and add in my vibrational energy. So energies are sums, the probabilities, and partition functions are products. It's been a while since I made this Kahoot. I'm going to be laughing at myself if that's the next question. But we'll see. No, it's not. Okay, so how many vibrational motions does a nonlinear molecule have? So you guys ought to be fast with that. Yeah, 3n minus 6 for a nonlinear molecule. And so how much for a linear molecule? 3n minus 5, yeah. All right, so it's time for the... Yay. KB with the, it looks like a little sea monster with the pacifier. It's kind of crazy, yeah. All right, good job, folks. Y'all have a great day.